So what we want to do is we're going to talk about RL circuits. We've already introduced the idea of an inductor. And so now consider an RL circuit. So for my circuit, what I want to do is I want to consider that we've got power supply, we'll just call it V0, and we've got inductor L, resistor R, and we have a switch up here that can go from position A to position B. So we're going to start off with a switch in position A. Now, we'll explain what happens to this in a moment, but we're going to start off saying after that it's been in this position for a long time. So current is going to want to go this way. We know that resistor resists change, but after a long time, we're in a steady state condition. So we're in equilibrium. So it's no longer resisting. And so remember, it's basically just a wire. It's a coil that's just a wire. And so all that we have is a voltage and a resistance. So that means the current in there is going to be equal to V0 over R. And so that will be the current, the steady state current after a long time. So then what I want to do is I'm going to throw the switch to position B. And then I want to know what happens at that point. So we know that the inductor doesn't like change. So as the current, because there's no longer a power supply in there, so the current's going to try to drop, but the inductor is going to have an EMF that resists the change. So the EMF of the inductor is minus L di dt. So it's going to resist any change, so it's going to temporarily keep the current flowing. Well, in order to get a circuit, the current's going to flow this way. Okay, and so what we want to do is investigate that current flow. So we'll do that by imagining starting right up here at the X at the top and doing a Kirchhoff loop going around in a counterclockwise direction. And so if you do that, then what you've got is you've got the voltage or the EMF on the EMF on the inductor, okay, minus IR equals 0. EMF on the inductor is minus L di dt. So minus L di dt minus IR equals 0. So we look at that and doing just a little bit of algebra, then what we find is that di dt equals minus R over L times I. Now, we've got a derivative proportionate to negative of the original thing we took the derivative of. And so we know from calculus that the sort of thing that does that is e to the negative something. And so that's going to be, well, we saw the same sort of thing when we did RC circuits. We saw that when we had a capacitor and it was discharging, then dq dt, it was equal to minus 1 over, minus RC times Q, and so that gave us the idea that e to the minus t over tau, where tau was equal to RC. So this is going to be the same sort of thing. So we're going to say that I is going to be equal to some I naught e to the minus t over tau, and so same solution right here, and tau in this case is going to be equal to L over R. So that's going to be the time constant. And so this is exactly the same analogous sort of thing as with the capacitor. So the current drops off over time. It's losing the energy, and so that means if you were to make a graph of this, that if you had current versus time, it'd start off at I naught. Now I naught is going to be whatever the current was initially in the capacitor when you threw the switch, and it's going to start dropping. It's not going to drop instantaneously. It'll drop pretty quick, but it will not be instantaneous. That's why anytime you have an electric motor or something and you just suddenly unplug it, then it will try to keep the current flowing, and you can actually build up quite a lot of charge. So in other words, if you got a vacuum cleaner or a power tool and you unplug it while the motor's running, you'll actually generate a very large spark because the inductance of the armature or the coils that are in the motor will try to keep the current flowing. Back to the initial setup though, when we had this and we had the switch and we had the inductor and we had the resistor, okay, position A, when you throw this to position A, then current wants to flow that way, but the inductor is going to have a voltage that resists the change. It's going to try to stop the current from flowing right away. And so in that case, what would happen is that you would have, again, a Kirchhoff loop start here and then go around. Then we've got V0, okay, minus the EMF across the inductor minus IR. Okay, and that's going to be equal to 0. So V0 minus a negative L di dt. Well, it's actually a negative, negative, negative. So it's a triple negative. Because what happens here is that the di dt is negative. So you need negative di dt. And so the negative of the negative of the negative makes just one negative right there. And so then minus IR equals 0. Now again, we saw a very similar equation to this when we looked at the capacitor as it was charging. And so you get exactly the same result here. You get that I is equal to I naught 1 minus e to the minus t over tau, where tau equals L over R again. So that would be in case that you are starting to have current go through the inductor. So if you're trying to increase the current in the inductor, then this is what you get. The I naught in this case is not initial I, it is the steady state I. So it is after everything has settled down. So for this problem, the I naught will be equal to V naught over R. All right. If we were to graph that, then what we would have is we'd have I, and then we would have T. And so right here, the origin, when you first close the switch, instead of suddenly having current, it would asymptotically increase approaching I naught. How quickly it asymptotically increases depends on the resistance. Or not the resistance, but on the inductance. So an inductor could be used as, for example, a surge protector, because it would resist a sudden surge or a sudden increase in voltage. And in fact, if you just had any circuit whatsoever, just any circuit, even our simple circuit that we talked about a long time ago, in which we have a V and an R, you close the switch, current starts flowing. Because current starts flowing, get a magnetic field in here. Because there's a magnetic field in there, you're changing the flux. The change in flux induces an EMF that way. Even this little tiny circuit right here would have a tiny bit of inductance and a self-inductance. And so what would happen is that naively you would think if you close the switch right there, okay, then what would happen is before you close the switch, there's no current, and then suddenly the current jumps up to V over R. But that's not what really happens. What really happens is that you close the switch right there, and what happens is there's no current, and then all of a sudden it asymptotically increases to V over R. Now, This is really not going to be as extreme as I've drawn it right there. It'll be like almost a step function like up here. But it's going to not be exactly a step function because there is going to be a little bit of self-inductance. How much depends on the circuit and the circuit design and the geometry of it. Obviously, if you loop things many times, then you create more inductance, and so that takes a longer response time until you reach the steady state. Every circuit is going to have a response time when you turn it on or when you turn it off. Because there's always going to be a little bit of inductance, they will never instantaneously become whatever it is that you wanted them to become. So they're going to take a little bit of response, and how much response depends highly on the amount of inductance, because the time constant is going to be related to the inductance of the circuit divided by the resistance in the circuit.